Good afternoon, class. Here's chapter 8, further application of trigonometric functions, section 8.5. Polar form of complex numbers, the complex plane, the Moivre's theorem. So we've looked at the law of sines, cosines, polar coordinates, equations and graphs, and now polar form of complex numbers. The objectives are plot points in a complex plane, convert a complex number between rectangular form and polar form, find products and quotients of complex numbers in polar form, use the Moivre's theorem, find complex roots. Again, properties of trigonometric functions. A unit circle has coordinates x comma y, cosine t, sine t. So cosine represents the x, sine represents the y, and the rest of them follow. All trigonometric functions are odd functions. That means f of minus x is minus f of x, except cosine and therefore secant, where f of minus x equals f of x, or cosine of minus x equals cosine x. We have fundamental identities such as Pythagorean identities, quotient identities, reciprocal identities. A right triangle, of course, a squared plus b squared equals c squared, Pythagorean theorem, and a plus b must add up to 90 degrees. Sine law, sine a over a, sine b over b, sine c over c, they are equal. Cosine law, a squared is b squared plus c squared minus 2bc cosine a, and you can solve for cosine a becomes b squared plus c squared minus a squared over 2bc. Circles with the center at the origin, x squared plus y squared equals r squared. At h comma k, a different location as far as the center is concerned, x minus h quantity squared plus y minus k quantity squared equals r squared. Polar coordinates. Well, we have the rectangular grid and polar grid. Polar axis is the same as the x-axis, and pole is the same as the origin. A point has coordinates x comma y or r comma theta. X squared plus y squared equals r squared, tan theta equals y over x, and as always you adjust it for the quadrant. Polar has coordinates r comma theta, rectangular x comma y, where x becomes r cosine theta and y is r sine theta. So if you want to go back and forth, those are the formulas that you use. Polar coordinates are not unique. So r comma theta is the same as r comma theta, and you can add 2k pi. If you want r to be negative, you add another pi. In other words, odd multiples of pi, where k is an integer. A rectangular grid, you have x comma y, for example, 1 comma 2. A polar grid, normally you have a circle centered at the pole or the origin, and you have a bunch of them. So if you want, for example, 2 comma pi over 4, first you locate the pi over 4 ray, and then you go 1, 2 tick marks. 5 pi over 4, and then you go 4 tick marks, 4 comma 5 pi over 4. That's rectangular versus polar. And you can put them together if need be. And there are some more points, as you can see. Again, with the case of a polar, first start with theta. Finally, the pole has coordinates 0, with theta being any angle will work. For graphs, just to remind you what we did, theta equals alpha, then y equals tan alpha times x is a line that goes through the origin. R equals a is a circle centered at the origin. or the pole, and has the equation x squared plus y squared equals a squared. R cosine theta equals a number, a constant, is the same as x equals a in a rectangular coordinate format, becomes a vertical line. R sine theta equals b is the same as y equals b. It's a horizontal line. And the following are all circles. R equals 2a cosine theta or minus 2a cosine theta. R equals 2a sine theta or minus 2a sine theta. Okay, they are all circles with the radius being half of 2a or half of the absolute value of that. The number sitting in front of cosine or sine, half of that. If it's cosine, the center is along the x-axis. If it's sine, it's along the y-axis. That's all. Now, if we have r equals a plus minus a cosine theta or a sine theta, looks like a cardioid. If it's a plus minus b cosine theta, depending upon the relationship between a and b, it's a lemma without inner loop if a is larger than b. And if a is less than b, there is an inner loop. The rows, if we have a sine of n theta or cosine of n theta, we have n pedal if n is odd, and we have 2 times that if it's even. And this is lemniscate when it's a squared cosine of double angle. So these are various graphs that we discussed in the previous section. And now the summary for section 8.5, the complex plane, the Moivre's theorem. Here's the summary. A complex number, everybody remembers a plus bi. It's the same thing, z equals x plus y I, where x and y are real numbers, and I by definition is square root of -1, which is an imaginary number. Okay, again, think about a plus bi, the same concept. Recall I is equal to square root of -1, I squared is -1, I cubed is -I, and I to the power of 4 is positive. The magnitude, also known as the modulus of z, is the distance from the origin to the point x comma y, and it's equal to the square root of x squared plus y squared over r. Z is x plus yi. Z bar, that means its complex conjugate is x minus yi, and again, z is equal to r, the modulus, x squared plus y squared, or the square root of z bar. Sometimes this is a plus bi. Remember that. That's the same thing. This is a minus bi. Everybody should be familiar with that in algebra. And recall a plus bi times a minus bi is a squared plus b squared. And just quickly to show you, remind you, remember a plus b, a minus b is a squared minus b squared. So this is a squared minus b squared I squared. I squared is -1. We get that one, just to remind you of that. I'm going to erase my work so we can continue. We are looking at the summary of the section. So we said x equals r cosine theta, y equals r sine theta. If r is greater than or equal to 0, theta is between 0 and 2 pi. We have the complex number in polar format, z equals x plus yi, r cosine theta plus I, r sine theta. Now the shorthand notation for this r cis theta, c stands for cosine, I of course is I, and s stands for sine. R cis theta, that's another way of writing. So we are looking at a rectangular grid. The x-axis would be the real axis, the y-axis would be the imaginary axis. This is called a complex plane, where r has the value of the modulus of z, which is the square root of x squared plus y squared, not much brand new. Z is x plus yi, or cis theta. This is the shorthand notation for r times cosine theta plus I sine theta. So r is cis theta, also equals to r equals e to the power of I theta. R squared is x squared plus y squared. Tan theta is y over x. Now, let z sub 1 be the first number, r1 cosine theta 1 plus I sine theta 1. Z2 be r2 cosine theta 2, I sine theta 2. In other words, this is r1 cis theta 1. This is r2 cis theta 2. Their product, how do we multiply? Simply put, multiply R1 and R2 and then add up their arguments. A shorthand notation Z1, Z2 is R1, R2, cis theta 1 plus theta 2. Division, if we want to divide Z1 by Z2, the shorthand notation R1 divided by R2, cis theta 1 minus theta 2. The Morse theorem says if you want to raise it to the power of n, raise r to the power of n, and then multiply the theta by n. In other words, z to the power of n is r to the power of n cis n theta. And of course, if you want to take the root, where w is r cosine of theta sub 0 plus I sine of theta sub 0, and you want n distinct complex nth root of w, n is larger than or equal to 2. You take the nth root of r, cis theta 0 over n plus 2k power n, and you choose k to be 0, 1, 2, all the way to n minus 1. This is the summary. We are going to make some sense out of each and every one of them by looking at the examples to make sure everybody is clear. By the way, this is 360 degrees k over n or 2k pi over n, depending upon whether we go with the radian format or degree format. All right, to get this started with a simple example, writing a complex number in polar form, plot and write complex number z equals square root of 3 minus I in polar form. Well, you go with a complex plane, and I'm going to show you, for example, 3 plus 2i, 3 to the right, 2 up. This is a plus bi. 3 plus 2i is here. So again, the x-axis is the real axis, the y-axis, the imaginary axis. So if we want this one, square root of 3 is about roughly 1.7. So it's 1.7 minus 1i. So you go about 1.7 to the right, and you go 1 down. So that would be the location. Okay, square root of 3 minus I. Roughly, this is not exact. This is an approximation. So first, plotting it. So again, this one to the right, minus 1. If it helps, put 1 here. Now, what is r? R is x squared plus y squared. So we are going to square this, and then negative 1 square it. As you know, this is 3. This is 1. They add up to 4, comes out as 2. Very straightforward, everybody. Tan theta, tan theta is y over x. So y is negative 1, and x is square root of 3. And it is important to pay attention to the quadrant, which is the fourth quadrant clearly. Never mind the negative. Square root of 3 over 3 gives you pi over 6. Therefore, this is minus pi over 6, or 11 pi over 6. So square root of 3 over 3, if tangent is square root of 3 over 3, is pi over 6. So z equals r cis theta. R is a 2 cosine of 11 pi over 6 plus I sine of 11 pi over 6. And that can be put in a simplified version, R cis theta, 2 cis 11 pi over 6. Both of them mean the same thing. I want to emphasize this is a shorthand notation for that. So a quick recap. A plus BI, you go A unit to the right, B units up. 3 plus 2I, you go 3 to the right, 2 units up. That's the location. In this case, square root of 3 about 1.7 to the right, minus 1 down, so roughly here. Again, this is not exact. That's as far as plotting points. R squared is x squared plus y squared. We find it to be 2. Tan theta is y over x, and we can find theta. Always pay attention to the quadrant. And you write the answer in shorthand notation, R cis theta. Very simple, everybody. So we're going to plot the point and convert it. Z is 2 cosine of 30 degrees plus I sine of 30 degrees. So in essence, you make up the 30-degree angle and you go 2 tick marks. That's the idea. So this is the real axis, this is the imaginary axis. And so 30-degree angles, and you go to 2 tick marks. Now, cosine of 30 is square root of 3 over 2. Sine of 30 is 1/2, everybody. So the 2's cancel out. We get square root of 3 plus I. This is the rectangular form. This is the polar form, and you're done. So first, how do you graph this? 30 degrees. And then how many tick marks? R units 2. Write the point in rectangular form. So this is given in polar form. Simply put, it means plug in. Obviously, you notice R is 3. Theta is 3 pi over 2. Cosine is 0. Sine is -1. So this doesn't do anything. This is -3i. So z equals -3i in rectangular form. Rectangular form. All right. Now find products and quotients of complex numbers in polar form. Z1 is R1 cis theta, shorthand notation. Z2 is R2 cis theta, 2. And we are going to multiply and we are going to divide. And we are going to prove this is the product. This is the quotient. So let's start with Z1, Z2, everybody. So we are going to multiply these two. We are going to show the product is R1, R2, cis theta 1 plus theta 2, the shorthand notation. So Z1 times Z2 is R1 cis theta 1 times R2 cis theta 2. Just write this one and write this one. First and foremost, R1 and R2, we do the product, we put R1, R2. And now we are going to distribute these two. Please understand, we are going to distribute this one over this one. That means cosine theta 1, cosine theta 2, cosine theta 1, I sine theta 2. We can put the I first. I sine theta 1 cosine theta 2 and I squared sine theta 1 sine theta 2. So we do the product. We distribute and we keep the R1 times R2 out. So this is the distribution. First thing first, notice this becomes minus because I squared is minus 1. That's the first thing I want everybody to notice. Then this one and this one we are going to combine, and these two we are going to combine. When we combine, so R1, R2 remains. Cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine theta 2, because I squared goes away, becomes it. And we're going to put these two together and we factor the I out. This becomes plus I. We can put this one first, sine theta 1, cosine theta 2, and this one second, cosine theta 1, sine theta 2. Why am I writing it in this fashion? I put this one first. Why did I do that? I want to remind you. What is sine of alpha plus beta? Sine alpha, cosine beta, cosine alpha, sine beta. I hope you recognize this one as sine of theta 1 plus theta 2. Cosine of alpha plus beta is cosine alpha, cosine beta minus sine alpha, sine beta. And I hope you recognize this as cosine of theta 1 plus theta 2. Believe it or not, that's the proof. And therefore, a shorthand notation, Z1, Z2 is R1, R2, cis theta 1 plus theta 2. In other words, if you want to multiply complex numbers in polar form, multiply their modulus, their magnitude, and then cis add up their arguments. So we proved the product works in this manner. We are going to prove the quotient works in the same manner as well. In other words, Z1 over Z2 is equal to that. Let's work it out. And as always, when you do that, the denominator can't be 0. So let's look at Z1 over Z2. And to prove that, we're going to start with Z1 over Z2, and we're going to write the Z1 at top, Z2 at the bottom. So the proof, Z1 over Z2 is this piece over that piece. We are going to use a trick or a technique, if you will, to take care of the business. We are going to multiply the top and the bottom by the conjugate of the denominator, which is the same thing, just change this one to a negative, cosine of theta 2 minus I sine of theta 2. So we're going to multiply the top and the bottom by. First of all, the bottom, I hope you recognize. When you multiply, I want to discuss the bottom first because it takes a second. You get R squared, and then this is A plus IB, A minus IB. It's A squared plus B squared or minus I squared sine squared. So R2, square this one, minus I squared. I'm going to show you again, although we've discussed that. So this one is minus I squared sine squared theta 2. These two just distribute. Okay, we are going to distribute it. I wanted to show you the denominator first. We are going to distribute this in a moment. So again, let me discuss the denominator first. This is plus, this is minus, minus becomes plus, and therefore the denominator is r squared times, what is cosine squared plus sine squared? 1, because they have the same argument. Cosine of theta 2 squared, sine of theta 2 squared, you're adding them up. So this is 1, r squared times 1. Let's look at this one. Let's multiply this one by this one. In other words, distribute cosine of theta 1, cosine of theta 2, minus I cosine of theta 1 sine of theta 2 plus I sine theta 1 cosine theta 2 plus and minus is minus I squared sine theta 1 sine theta 2. So let's just distribute. So as I mentioned, the denominator becomes R2 times 1. What happens here, we're going to combine these two. And how do we combine that? Minus I squared changes to plus, right? Because I squared is minus, minus times minus is plus. So we are looking at this piece, cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2, when you combine these two. And then when we combine these two, we take the I out. If I take positive I out, I put this one first, sine theta 1, cosine theta 2, minus cosine theta 1, sine theta 2. Again, what I did, I put R1 over R2 outside the brackets, reminding you of that. So this is cosine of theta 1 minus theta 2, and this is sine of theta 1 minus theta 2. And that's exactly what we wanted to prove, that the ratio is R1 over R2 cis theta 1 minus theta 2. So we proved that one as well. Now, if Z is 3 cis 20 degrees and W is 5 cis 100 degrees, find the product and the quotient. Let's look at the product. R1, R2 cis theta 1 plus theta 2. Therefore, it's 3 times 5 cis 20 plus 100, according to the formula, and we have already proved that. So this is 15 cis 120 degrees. And we don't have to continue because we want it in polar format. We found it, we are done. Of course, this means 15 cosine 120 degrees plus I sine 120 degrees. This is a shorthand notation. Let's find the quotient. R1 over R2, 3 over 5, cis theta 1 minus theta 2, 20 minus 100. And so this is negative 80. And let's make it positive. Because it's in degrees, I'm going to add 360 degrees. If it was in radians, I would add 2 pi. So I get 280 degrees. So 3/5 of cis 280 degrees. So a quick recap. You are given two numbers in polar form. You want to multiply. You multiply their modulus or magnitude. You add up their arguments. You want to divide them. You divide their modulus, 3 over 5, and then you subtract. So 20 minus 100. Use the Morse theorem. write 2 times cosine of 15 degrees plus I sine of 15 degrees to the power of 4. Well, according to the Moivre's theorem class, if you have z equals RC theta and you want to raise it to the power of n, you raise the modulus to the power of n, and then you multiply this one by n. So z to the power of 4, you're going to raise 2 to the power of 4. So first, let's just write it the way it is. This to the power of 4 means we're going to raise 2 to the power of 4, and we're going to multiply this by 4 according to this formula. And so this 2 to the power of 4 is 16. 4 times 15 is 60. Cosine of 60, 1/2. Sine of 60 is square root of 3 over 2. 16 divided by 2, 8. So it's 8 plus 8 square root of 3i. It's very straightforward, everybody. A quick recap. You want the Moivre's theorem says if you want to raise a polar number to any power, you raise the modulus to that power and then you multiply the argument by that power. That's exactly what it says here, and this is what we've done. And you can get to the answer in no time. All right, let's move on. We want to raise 1 minus I to the power of 10. We want to find z to the power of 10. Now, please understand, if I want to raise 1 minus I the way it is to the power of 10, it takes a long time. But I'm going to put it in polar form, and it becomes fairly nice and easy. To put it in polar form, I'm going to put it in the form of z equals RC theta. I need the R, which is square root of x squared plus y squared. Please understand, x is 1, y is negative 1. Okay, x is 1, y is negative. So this is 1, this is 1 becomes 2, so it's square root of 2. Now I need to find tan of theta is y over x minus 1 over 1 or negative 1. So theta is minus pi over 4. Now you can keep it as negative, or if you want, add 2 pi. Okay. And it becomes 7 pi over 4. It's not a big deal. So z, which is r cis theta, is square root of 2 cis negative pi over 4, or cosine of negative pi over 4 plus I sine of negative pi over 4. So this is the polar format. Again, if you can add plus 2 pi and use 7 pi over 4. Makes no difference. Okay. So I want to raise this to the power of 10. According to the Moivre's theorem, okay, we are going to raise this one to the power of 10. Okay, this one. And then we're going to multiply the argument by 10. So we just do that. Of course, when you want to raise square root of 2 to the power of 10, is the same as 2 to the power of 5. When we multiply these two, 4 becomes 2, 10 becomes 5. So I hope you see that This is negative 5 pi over 2. Now, 2 to the power of 5 is 32. If I, because I want to bring it, make it easier to understand. If I add 2 pi, which is 4 pi over 2, I get minus pi over 2. And I hope you know that cosine is 0. Sine of pi over 2 is positive. Sine of negative pi over 2 is negative 1. So 32 times negative 1 times I, negative 32i. So I hope you realize how fast we could raise this to the power of 10 using the polar format. And that's really the idea, the key, okay? So 1 minus I to the power of 10 is simply negative 32i. A quick recap. Z is given in rectangular format as a complex number. We put it in polar format, so it makes it easier to raise it to the power using the De Moivre's theorem. What about this one? Write the expression in standard form of a plus bi, and we want to raise this to the power of 6. It is in polar form, so it makes life easier. If you want to raise this to the power of 6, you're going to raise this to the power of 6 and multiply the argument 10 degrees by 6. R to the power of 6 cosine of 6 theta plus I sine of 6 theta. So let's raise this to the power of 6. That means square root of 3 to the power of 6. And let's multiply this by 10 by 6. So obviously this becomes 60 degrees. This becomes 60 degrees. Square root of 3 to the power of 6 is 3 cubed with me. Which is 27. Since they want it in standard form or rectangular format, (27 times 1/2, 27 halves, plus 27 square root of 3 halves, I. By the way, sometimes they put the I in front or in between just to make sure it's not under the radical, okay? Just in case. Just want to make sure that everybody is familiar with the concept. Find complex roots, find complex cube root of negative 4. So complex roots. Let W be R cosine of theta sub 0 plus I sine of theta sub 0, where n is a number that is either 2 or larger and has n distinct complex roots. Z sub k, that means the roots, is the nth root of R, because you want n distinct complex root. And then you are going to divide this by n and plus 2k pi over n. K is an integer, everybody. That is the methodology where k is any number from 0 all the way to n minus 1. Why n minus 1? Because if you go with n, you repeat the process. So in this case, we are going to quickly write this in polar format. Minus 4 is 4 cis pi, or 4 cis 180 degrees. Sometimes you go with degrees, sometimes with radians, but degrees may be easier. And n is 3 because, why n is 3? Because it says cube root, everybody. Why is this 4 cis pi? I want you to know that if you have a positive number, for example, I just want to make sure that if it was positive 4, or would be 4 cis 0 degrees. 0, because remember, this is 0 degrees, right? And on this side is 180 degrees or pi radians. That's why if you have so this is 1, 2, 3, 4. This is 1, 2, 3, 4 on the negative side. So any positive number, any number that is positive along the x-axis would be the same number cis 0. Any negative along the x-axis. So any just basically any real number, because it's not a complex, it just has a real part 4 and the complex part is 0. So 4 cis 0. If it's minus 4 cis pi. If it's minus 8 cis pi. Just a general form. So let's erase the word here. All right. So we are going to write cube root of 4. Okay, cube root of 4. Cosine of 180 degrees divided by 3 plus 360 degrees times k divided by 3. The same thing for this. Okay. This one becomes 60. This one becomes 120 degrees times k. And k, because we want 3 of them, cube roots, is 0, 1, 2. Again, if you go with 3, it repeats itself. Okay. So first, when we go with 0, basically this goes away. So the first one would be cube root of 4, cosine of 60 plus I sine of 60. If I put 1 here, I get 120 plus 60 is 180. So cube root of 4, cosine of 180 plus I sine of 180. Again, maybe the shorthand notation, this means cube root of 4 cis 60 degrees. The other one would be cube root of 4 cis 180. Now, if I put 2, I get 240 plus 60 is 300. So cube root of 4 cosine of 300 plus I sine of 300. In other words, notice the magnitude, or R, is square root of x squared plus y squared. So all cube roots have magnitude of cube root of 4. The argument 60, 180, and 300 degrees equally spaced. So if you divide 360 degree by 3, the space between them is 120 degrees. By the way, again, if you choose k to be 3, we want the cube. The third one, if you choose n 3 times 120 is 360, in essence gives you 63 back, 60 degrees back. That's why we don't. And so if you go with that, all 3 points are equally spaced on a circle of x squared plus y squared equals cube root of 4 to the power of 2. So this is a circle. The radius is cube root of 4. And this is 60 degrees, 180 degrees, 204 degrees. So, for example, complex cube root of 1 would be 1 cis 0. And what happens is that we basically replace the cube root of 4 with 1, because cube root of 1 is also 1. Okay. So we have those. And by the way, you can replace the cosine of 60 with 1/2, sine of 60 with square root of 3/2, and you can find those numbers. Now, one thing that I want to make a point of, because this was negative, it doesn't start with the x-axis, but it starts here. This one is positive 1, so it starts from the x-axis because the angle is 0. Okay. I hope that's helpful. Plot 3 minus 4i in the complex plane and write it in polar format. Let's go with degrees. Okay. So the very first thing we want to do, we are going to go 3 units to the right, 4 units down. 3 units to the right, 4 units down. 3 minus 4i, z equals 3 minus 4i. So this is the angle. So tan of theta is y over x minus 4/3. So the angle is this is not a common arc, this is the tan inverse of that. And tan inverse of minus 4/3 from the calculator gives us roughly minus 53.13 degrees. And normally we want positive. So all you have to do, add minus 53.13 degrees, add 2 pi, in this case 360 degrees, because we're going to go with degrees format. So 360 minus this is 306.87 degrees, or is square root of x squared plus y squared. That means 3 squared plus negative 4 squared under the radical, and this is 9, this is 16, and therefore this is 25, comes out as 5. So z equals r cis theta, x plus yi, that means 3 minus 4i equals 5 cis this number, 306.87 degrees. Again, I like to go with the shorthand notation. Either way is fine. Please understand they both means the same thing. So z equals 3 minus 4i equals 5, 6, 306.87 degrees. Use the Moivre's theorem to write 2 plus 2i to the power of 6 in standard form a plus bi. Well, if I want to raise this to the power of 6, I have to do that, multiply this by itself 6 times. Instead, I'm going to put it in polar, raise it to the power of 6, bring it back. So first and foremost, we need a couple of things. We need the r, which is square root of x squared plus y squared. So I'm looking at just this number. Never mind to the power of 6. So this number, 2 plus 2i. So this is 2 squared plus 2 squared under the radical. 4 and 4 is 8. So square root of 8. I hope everybody knows this 2 square root of 2, because first of all, we are looking at this number, okay? And this is square root of 4, square root of 2, and 4 comes out as 2. Then tangent is tan inverse of 2/2, tan inverse of 1, or simply pi over 4. So 2 plus 2i is r cis theta, 2 square root of 2, cis pi over 4. Cis pi over 4, or cosine of pi over 4 plus I sine of pi over 4. I want to raise this to the power of 6. So let's raise it to the power of 6. That means I need to raise this to the power of 6, and then I need to multiply this by 6 according to the Moivre's theorem. Now, 2 square root of 2 to the power of 6. By the way, if you just raise it to the power of 2, I hope you know 2 squared becomes 4 times 2 is 8. So this is the same as 8 cubed, okay? Just so you know. It's 512, 6 times power 4, 6 power 4, 3 power 2. As you know, cosine is 0, sine is -1. So 512 times 0 minus I, or minus 512i. In other words, if you want to raise this to the power of 6, it takes quite a while. Putting it in a polar format and bringing it back, it goes very fast. Find product and quotients of complex numbers. Z is given as 3 cis 130, W is 4 cis 270, and we are going to find their product. Well, according to the formula, R1, R2 cis theta 1 plus theta 2. So R1, R2 would be 3 times 4, and then cis 130 plus 270. Again, whether you go with the shorthand notation or a long way, either way makes no difference. 3 times 4, 12. 130 plus 270, 400. Now, because 400 is larger than 360, if we subtract 360 or add 360, makes no difference. We subtract and we get 40. So note 40 and 400 are coterminals, 40 degrees and 400 degrees. So you can write it in this format or just write 12 cis 40. That might be easier or nicer to write. I don't know. You just figure out what's the shorthand notation works out fine. All right. Find the complex cube root of -1 plus square root of 3i. Please understand I is outside. Leave the answer in polar form and let me erase. In polar form, use degrees. Okay. So the first thing is to write this in polar form. So we need the r, which is x squared plus y squared under the radical. So -1 quantity squared, square root of 3 quantity squared. This is 1, this is 3, and it becomes 4, and therefore comes out as 2. So this is negative, and this is positive, the second quadrant. Tan inverse of y over x. Theta is tan inverse of y over x. By now we know that, which is minus 60. In the second quadrant, 120 degrees. So this complex number in polar format would be 2 cis 120. 2 cis 120. And again, or 2 cosine of 120 plus I sine of 120. We want to Find the complex cube roots according to this will be the nth root of r, that means the third root of r, the third root of 2, and then cosine r cis theta sub 0. So we are going to divide this one by 3 plus 360 degree times k divided by 3. You divide this one, you get 40. You divide this one, you get 120k. And again, remember, you want the cube root, you go with k equals 0, 1, 2, and no more. If I put 0, this simply goes away. So R is 40 degrees. If I put 1, I get 120 plus 40, 160. I get R is 160. R is cube root of 2. And if I put k equals 2, 2 times 120 is 240, and 40 is 280. So R is 280. R is cube root, of course. We're done. I just want to quickly show you what we just found. It's cube root of 2 times this 40, this 160, 6 280. So all 3 points are equally spaced on a circle of x squared plus y squared, having the radius cube root of 2, cube root of 2 quantity squared. So take a look. X squared plus y squared is cube root of 2 quantity squared. One is at 40 degrees. Okay. Again, one is at 160 degrees and one is at 280 degrees. Now, I'm going to quickly explain how this De Moivre's theorem happened. I'm going to show you a couple of, steps for that, but it's proof by induction. So I'm going to do 2 of them for you. So De Moivre's theorem, we say if z is r cosine theta plus r cis theta, z to the power of n is r to the power of n cis n theta. We want to prove that by looking at n equals 2. So we raise this to the power of 2. Never mind what r is, just in this case, r is just 1. So if I want to raise this to the power of 2, I'm going to multiply it by itself. So this is cosine squared. So when you raise it to the power of 2, this is squared plus 2i sine theta cosine theta and minus sine squared theta. We are raising it to the power. And of course, this is cosine squared theta plus 2i sine theta cosine theta minus sine squared theta. And you get cosine of 2 theta is cosine squared minus sine squared, everybody. Cosine squared minus sine squared is cosine of 2 theta plus I sine of 2 theta. Because look at this one. Without the I, everybody. If you ignore the I, 2 sine theta, cosine theta is sine of 2 theta. So I sine 2 theta. So we proved that for n equals 2. For n equals 3, you're going to raise it to the power of 3, which means you are going to multiply it in this fashion. And this one, we already have it here. So we're going to replace it here. So we are going to replace it here. And now cosine theta, cosine 2 theta, cosine theta times I sine 2 theta, I sine theta times cosine 2 theta, and I sine theta times I sine 2 theta. You multiply them, you distribute them in this fashion. So this one and this one, this one and this one. And you put together these two. I hope you see that cosine theta, cosine 2 theta minus sine theta, sine 2 theta. This is cosine of theta plus 2 theta. And this one, if you factor the I out, sine theta, cosine 2 theta plus cosine theta to sine 2 theta, be sine of theta plus 2 theta as well, which is cosine of 3 theta plus I sine of 3 theta. And you can, I'm going to leave it for you to prove that it works for n equals 4. And then that is the proof that it works for n.